Today we're going to learn how to integrate scalar valued functions over curves. So what is that? Before I can answer that, let's go back and see what we know how to do. If we have an interval I on the real line, we can integrate a function over that interval, and it's pretty straightforward. If we have a function f of xy, imagine it maybe being a surface in space, we can integrate f over a region in the plane. Sometimes finding the limits on that integral will be difficult, but our dA is not difficult. It's either going to be dy dx, dx dy, or if you're doing polar, r dr d theta. If we're looking at triple integrals, then the dv, their differential here, if you're using Cartesian, it's dz dy dx, or cylindrical r dz dr d theta, or you could even do spherical. So what's new today is the ds. S is arc length, and we're going to learn how to integrate a function over a curve in space. But first, let's look at three applications. If you integrate a function f of xy over a curve in the plane, then you can interpret that as the area of the curtain formed that you see here. Now, why is that? If you take this curve and break it into little line segments, each of length delta s, and then take a sample point in each interval and evaluate the height of the function at that sample point, that will give you a rectangle. And the area of that rectangle is the height times the width. And then you keep doing that and you add up all your rectangles, and then you take the limit as the number of rectangles goes to infinity. You can also use a line integral to evaluate the length of a curve. You can simply take the value of the function to be 1, and then the area of your curtain here is the length of the curve times the height, but the height is just 1, so you get the length of the curve. And finally, you can compute the mass of a wire if you're given the linear density. So the linear density is mass per unit length, and so if you times by length, you get mass. Okay, so how do you evaluate a line integral? What's different here is the ds and the c. So ds, again, s is arc length. That can be a little bit tricky, but don't worry, we have a way around that. We can replace ds with the length of r prime of t dt, and I have a short description of why you can do that here. So let's just jump right into the PEACE acronym that we use to evaluate a line integral. And this will work for vector fields too. So 1, parameterize your curve. Typically, you're going to use your Bible to do that. 2, compute your ingredients. Those are the things that are going to go into your integral. And 3, evaluate your integral. That's usually the easy part. Okay, so let's do it. We want to evaluate this function over this curve, which happens to be a line segment. So step 1, parameterize. So we're going to use the Bible to do that. R of t is, I'm using this formula right here, and my x naught, y naught, z naught is 1, 2, 2, and x1, y1, z1 is 0, 0, 0. The order is important. So if I use that Bible formula, I get 1 minus t, 2 minus 2t, and again, 2 minus 2t for z. And t, for line segments set up this way, always goes from 0 to 1. Okay, now we need our ingredients. We're going to need r prime of t, because we need its length. So r prime of t is -1, -2, -2. So the length of r prime of t is the square root of 1 plus 4 plus 4, which is the square root of 9, which is 3. We're also going to need f of r of t. Again, I'm looking over here at this formula, and I'm seeing the ingredients I need. I need the length of r prime, and I need f of r of t. So f of r of t, I get by looking at f up here, and everywhere I see an x, I put 1 minus t, because this is my x. This is my y, and this is my z. So we start with x squared, which is 1 minus t, quantity squared, and then we're going to subtract y. Y is 2 minus 2t, and then we're going to add 3z. And z is, again, 2 minus 2t. Now, we're going to have to integrate that, so we're going to have to multiply it out and combine like terms. And if you do that, you can check me on this. You get t squared minus 6t plus 5. All right, so now we can set up our integral. 3. The integral over c of f ds is integral from 0 to 1. F of r of t is t squared minus 6t plus 5. And then the length of r prime of t is 3. and that's dt. So there's my integral, and you probably don't want to see me go through the arithmetic of evaluating that, but it's 7. Okay, let's do one more, but this will just be a setup. We're already given the parameterization here, and we're given linear density, and we want to find mass. So in my formula to the right, my rho is F. So step 1 is done. Step 2, we need r prime of t and its length. So r prime is -2 sine t, 2 cos t, and 2. So the length of r prime of t is square root 4 sine squared t plus 4 cosine squared t plus 4. Now, I can factor a 4 out of these two terms, and then cosine squared t plus sine squared t is 1, so I get square root of 8. All right, I need f of r of t, which is actually rho. So rho of r of t, I look up here at my formula for rho, it's 1 plus z. So I want 1 plus, my z is over here, 2t. So finally, my setup is the integral over c of rho ds is integral from, the parameterization was from 0 to 6 pi, and then rho of r of t is 1 plus 2t, and then length of r prime was root 8, and dt, and that's it. And that would be fairly simple to evaluate. All right, I want to mention 4 interesting properties of line integrals. Additivity, this C1 plus C2 is notation for unions. So if you want to go over one curve and then another curve and they have different parameterizations, you can just do those as 2 separate integrals. Properties 2, 3, and 4 I can illustrate with the curtain application. So if we jump over here, independence of parameterization. There are many ways to parameterize a curve. However, the area of this curtain is going to be the area of the curtain no matter how I parameterize it. So I could even go backwards and the area is still going to be the area. And then property 3, dependence of path. Well, if I have a different curve down here in the plane, I'm going to get a completely different curtain. And so it makes sense that the line integral is going to depend on the curve you choose. It's just not going to depend on how you parameterize it. And so back here, this notation, -c, just means you're running c instead of from A to B, you're going the other way from B to A. So we're going to end with 2 more formulas, line integral with respect to x and line integral with respect to y. So they're slightly different than the one we just covered. And the way you can tell which formula to use is you look at the differential. Is it ds, dx, or dy? And the dx, dy, a lot of times we'll combine them into the same integral. And so I'll show you an example of that. Let's set up this line integral, which is a combination of a line integral with respect to x and y. Okay, so we're going to start out the same. We're just going to use different formulas on step 3. So 1, we need to parameterize our curve. So our curve is over here. It's f of x equal x squared. So using the Bible for parameterizing a function, this is going to be, we're going to let x be t and y be f of t, which would be t squared. And t goes from a to b. A is -1 and b is 2. So this is going to be my x and this is going to be my y in the formulas you see to the right. Now we're going to need r prime of t. We won't need its length, so we're not going to do that. We're just going to find the derivative, 1, 2t. And so this is my x prime, and that's my y prime. All right, and so I'm going to separate out those 2 integrals at first. We have the integral over c of y cubed dx. I'm going to add on the integral over c of x dy. And I'm going to use the 2 formulas over here in the box. The only thing you have to be careful about is your f is different. In this integral, your f is y cubed, and in this integral, your f is x. Okay, so here we go. I guess we're up to step 3 now. This is equal to, the first integral goes from -1 to 2, and y cubed. So I look up here and I see y is t squared, so that's t squared cubed. And then I replace the dx with x prime, which is 1 dt. And then for my second integral, again, I go from -1 to 2. And now my f is x is t, and replace the dy with y prime of t dt, which is 2t dt. And let's do final cleanup here. I'm going to combine them back into one integral, -1 to 2, and you could keep them separate. This is going to be t to the 6th plus 2t squared dt. And that's it. Okay, and that's the end of this section.